Hi, I'm Ms. Hall, and this is Lesson 86, Applications of Compound and Disjoint Events. Example 3, using a formula to find probability of A and B. Out of 200 students in a senior class, 113 students are either varsity athletes or on the honor roll. So the probability of A or B is 113 out of 200, where A is varsity athlete and B is honor roll. There are 74 seniors who are varsity athletes. So the probability of A is 74 out of 200. And 51 seniors who are on the honor roll. The probability of B is 51 out of 200. What is the probability that a randomly selected senior is both a varsity athlete and on the honor roll? So the probability of A and B is what we are trying to find. So we can remember our probability formula from lesson 85, which is that the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. And we have the probability of A or B is 113 out of 200 equals 74 out of 200 plus 51 out of 200 minus x. Now I can solve for the unknown. 113 over 200 equals, that is a 5, 125 out of 200 minus x. Then move x to the left side to make it positive. X equals 12 out of 200. So we have the probability of A and B equals 6 out of 100. I can go lower. 3 out of 50, which equals 0.06, which equals 6%. Using more than one probability rule. In the first 4 sections of this chapter, you have learned several probability rules. The solution to some real-life problems may require the use of 2 or more of these probabilities rules as shown in the next example. Example 4. The American Diabetes Association estimates that 8.3% of the people in the United States have diabetes. Suppose that a medical lab has developed a simple diagnostic test for diabetes that is 98% accurate for people who have the disease and 95% accurate for people who do not have it. The medical lab gives the test to a randomly selected person. What is the probability that the diagnostic is correct? We're going to begin by drawing a tree diagram. The top will be the population of the United States. And we're going to split that population into people that have diabetes and people that do not. 0.083% of the population has diabetes. I'm going to call this event A, and I'll label has diabetes. So if 8.3% have, that means 91.7 or 0.917 do not have. This is the complement of A. Do not have diabetes. Okay, that was my first level. Now, the diagnostic test for diabetes is 98% accurate for people who have the disease. So if you have diabetes, this test is 98% accurate. I'm going to call that B. Accurate. 98% accurate means it's 2% inaccurate, or the complement of B. Inaccurate. And 95% accurate for people who do not have it. So if you do not have diabetes, the test is 95% accurate or 5% inaccurate. Right? This is accurate, this is inaccurate. And we want to know is what is the probability that the diagnosis is correct? We want to know the probability of B. Right? B is the diagnosis is correct. So we're going to have to find the probability of A and B. Yep. A and B plus the probability of the complement of A and B. So we want to know whenever the test is accurate, and there's two branches that lead to an accurate test. That is having diabetes and getting an accurate result, or not having diabetes and getting an accurate result, right? We're trying to figure out probability that the diagnosis is correct. Not that you have diabetes, but that the test is correct. And so on our next level, the probability of B is to find the probability of an AND event. You find the probability of the first times the probability of the second, B, given that the first has happened. We'll add that to the probability of the complement of A times the probability of B given the complement of A. Now I can fill in all the numbers. We have 0.083 times 0.98 plus 0.917 times 0.9. And when we multiply that, those two multiply each pair and then add them, the probability of B getting a correct diagnosis is 0.952, which is 95.2% accurate. That is the probability that the diagnosis is correct.